Hello, good morning. My name is Dr. Felusha Gumbiade. I'll be the one that will be teaching you the Lewis structure, the drawing of the Lewis structure this morning. The class is being zoomed and being live streamed. So whichever option you prefer, you can stay with. I have sent the link to the live stream to you via the chat box. I will believe that you should be able to copy it from the chat box and send it to your colleagues that may not be able to stay in the Zoom link. Dr. Abayomi took time to teach you the covalent bonds, the electrovalent bond and the covalent bond in the last two sessions. So today I will be teaching you how to draw Lewis structures. There are some of the issues that we need to be abreast of. We need to know when we are drawing Lewis structure, and those issues we are going to interrogate them, and from there we will move forward. In drawing a valid Lewis structure, you want to understand the principle of octet rule. I know you've been taught the principle of octet rule. However, there are some exceptions to the octet rule. Those exceptions start after the third period, which is the third full rule. The second full rule of the periodic table. The full rule of the periodic table, if you look at the periodic table, is the second period. The first period, where you have hydrogen and helium, they are not the full role of the periodic table. So we will be looking at how to undo Lewis structure. We will start with the full role of the periodic table that follows the octet rule. Then we will also look at how to draw structure where you have single bonds, double bonds, or triple bonds. You want to do the Lewis dot structure of a single bond. What are the rules and how do you go about it? Then we'll be dealing with when you have isomers. How do you draw the Lewis structure of isomers? You know that isomers have the same composition but different constitution. So we will be looking at how do we deal with that. Then we will also look at how to deal with resonance structure. When you have a molecule of resonating bonds, how do you address or draw such structure? Then we would look at how to do formal charge, how to calculate formal charges. And which type of formal charge, or which from the calculation of formal charge, we will know which one is stable or which one is not stable, which one is preferred. Formal charges are calculated when you have resonating structure and you want to deal with that. Then finally, we will look at those ones that violate octet rule. There are molecules that violate octet rules, those ones that have odd structure, odd number of electrons, those ones that have electron deficiency, or those ones that have more than 8 electron in their or 8 bonding, 8 electrons, which means they have more than 4 covalent bonding. Those are the things that we will be looking at in the course of this class today. Sorry, please, I needed to exit. So in any case, the drawing of the Lewis structure will be what we'll be looking at. Now, Lewis structure was proposed by G.N. Lewis in 1916. And what is the principle is that there is an atom that will be the central atom. And it proposed that other atoms will now combine with it to form a stable electronic configuration. So what you want to achieve is a stable electronic configuration, but there will always be a central atom that the other terminal atoms will join with. Now, maximum stability will result from when you have an isoelectronic configuration with a noble gas. What does that mean? Noble gas has 8 electrons in the atomos shell. So you can only have a stable molecule when the atomos shell has the electronic configuration that is similar to a noble gas. So which means that if oxygen, for instance, want to have a complete electronic configuration that is of the noble gas, oxygen has 6 electrons in its outermost shell, so which means that oxygen will pick up 2 other electrons by sharing. In this case, we are dealing with molecules, we are not dealing with electron transfer. So by sharing, it will pick up 2 electrons to give us 8 in the valence shell. So we'll be looking at the details and examples of all this as we go on in the course of the class. Now, an electron pair that is shared between 2 atoms constitute what we call the covalent bond. Now, in covalent bonding that you did within the week, you are told that there are pairs that are bonded electron and pairs that are non-bonding electron. The non-bonded electron pair are the lone pairs. They are the lone pairs. So within the valence shell, any electron that is not bonded is the lone pair, while the bonding electron is a covalent bond that is formed between the 2 atoms that are sharing with each other. So in drawing a Lewis structure, electrons are represented with dots, and they are the structure is only drawn with the valence electron. You cannot use the innermost or the inner electron to draw the Lewis structure, because the Lewis structure is based on bonding, and it's only the covalent, the valence electron that are used in bond formation. So in this case, each electron that is represented in a Lewis structure is represented with a dot, and that dot is representing the valence electron. So in any case, if I want to draw a Lewis structure of oxygen, I will have 6 dots. Nitrogen, 5 dots, because those are the valence electron in those atoms. Then, when you use the periodic table, you can use the periodic table to determine the number of dots. Each valence electron is a dot, as previously explained. Now, the number of valence electron is equivalent to the group that the elements belong to in the periodic table. So hydrogen will have 1 valence electron, which represents the group 1 that it belongs to, and the fact that it has 1 valence electron at the atomos shell, so it will be 1 dot. Helium will be 2 dots. Lithium will be 1 dot. Lithium has a periodic, the atomic number 3, but in the electronic configuration, it has 1s2 and 2s1, which means that it belongs to group 1. So the valence electron is a 2s1, which makes lithium to be in group. So when we want to draw the valence, the Lewis structure of lithium, we use a single dot. Beryllium will be 2 dots, boron will be 3 dots, carbon will be 4 dots, nitrogen 5, oxygen 6, fluorine 7, and neon 8, showing us each of the electrons that is at the valence shell. So now the number of electrons in the valence shell, as previously mentioned, is the number of bonds that is in the the number of group, or the group number that the element belongs to in the periodic table. So for better understanding, you will see from the diagram below that you have the periodic table as presented. You have hydrogen as 1, lithium as 1, sodium as 1, potassium as 1, because they belong to group 1. They all belong to group 1. Then group 2, you will see beryllium having 2 dots. Now, in placing the dots, it is very instructive for you to know that each dot is placed at different position on the. So if I want to, for instance, explain, if I want to write for beryllium, it is inappropriate for me to put the 2 dots like this. This is wrong. Rather, I will put the 2 dots in 2 different positions on the periodic, on the element. So I will put 1 dot at one side and another dot at the other side. So in putting the dots, I will rather, the appropriate rule is for you to put 1 here, 1 dot here, and the other dot there. If I want to write for carbon, you will see that the one of carbon is written with, sorry, please, just to show you, the one of carbon and the one of silicon is written as 1 each for the 4 different cardinal points. So you will not put 2 with each other in the course of drawing a Lewis structure. You will position your electrons at the 4 region. It is when the east, west, north, and south region are all filled, that you will then start to add the subsequent electron to the next region. So if you look at group 5, you would see that you have each dot on the 4 region first, then you start to add the next one at any position you so desire. Then if you look at group 6, you have the 4 in the 4 region initially, then you have the next 2 coming to add to the already established 4, and you continue like that until you get to the end. So in the drawing of Lewis structure, sorry, I want to clean the. So in the drawing of Lewis structure, you must be careful to position your electron dots, the dots that represent the electron, appropriately based on the number of electron in the valence shell, based on the number of electrons in the valence shell. Now, having established that, the next that we need to also know is that there are also rules that guide the drawing of the drawing of Lewis structure. After you have put on your valence electron, then you will need to join them with lines that represent the bond. Now, the electron, we have already established that the electron are of two types. You have the core electron, which is the electron in the inner part, and you have the valence electron. The core electron are the ones in the inner shells, while the valence electron are the ones at the outermost shell. Now, the number of valence electron is equal to the group. I've already mentioned that. And when you have representative elements, which are the S element, S block, and P block elements, their number of group is corresponds to the valence electron. So if you have 5 valence electron, it means that element is a group 5 element. So now, as previously explained, you put the first 4 dots at each cardinal point, at each side, each 4 side, the east, north, the east, west, north, and south of the atom. You don't put 2 together. So if there are more than 4, then you will now start to add that electron to the to that point until you get to the octet rule. Now you have two dots with each other, 2 electrons with each other in your Lewis structure. You have what we call a lone pair. So that information is very essential in chemistry. That lone pair is the basis for the coordinate covalent bond, because in coordinate covalent bond, you have a lone pair of electron donated to an electron deficient region. So that information is very important for you to note. Now, ionic compounds are produced when you have transfer of one electron into another. So we know that from electrovalent bonding that we've discussed earlier in the class. And covalent bonds are produced when you have sharing of one or more electrons. So in any case, for every line in a Lewis structure, every line represents a pair of electron, a bonding pair of electron, not a low pair this time around, a bonding pair of electrons. So in any case, when you see a Lewis structure, you should be able to interpret what the total number of electrons around the Lewis structure is based on the fact that each bond is a bonding pair, and each electron pair that is not bonded, that is not used to form a bond, they are the lone pair. So covalent molecules, as previously said, is because you have shared electron from 2 atoms. Those 2 atoms can be atoms of the same element or atoms of different elements. For instance, if you have O2, oxygen molecule, that is atom of the same element. N2, nitrogen molecule, atom of the same element. But if you have a CO, that is atoms of 2 different elements and the like of that. So molecules are compounds formed when you have covalent bonding. Covalent bonding produce molecules. And during Lewis structures are drawn from molecules. And as previously said, they are drawn from molecules to achieve octet when you are drawing it. Now, there are some basic rules that we will need to get ourselves acquainted with. Number 1 of the basic rule is that there is always a central atom and there are terminal atoms when you are drawing a Lewis structure. And we need to know which type of atom can be central atom. Now, anytime you are writing a Lewis structure, the central atom is always the one you write first, except in the case of acids. We are going to speak to them, and also in the case of hydrogen molecules. In the case of hydrogen molecules, you don't write the terminal, the central atom first. But in most molecules, the central atom is always written first. So the bedrock rule for writing Lewis structure for the first row of the periodic table is for you to understand some of these principles of the fact that you have central atom and you have the terminal atom, and also for you to know that you are using it to achieve an octet, except in the case of hydrogen, where you are trying to achieve a doublet for hydrogen, because hydrogen is an s orbital that has only one s orbital, which is 1s1. So it can only achieve a stable electron configuration when you have 1s2, which is the doublet. Then in any case, you can have only a single line when it comes to hydrogen, because hydrogen will only achieve a single bond to form a doublet, which is the stable electronic configuration of hydrogen in the periodic table. So the last rule that I mentioned is the fact that when you have the when you want to write the Lewis structure, you write based on the principle of central atom and terminal atom. Now, the central atom is the one that holds all the elements, all the other terminal atoms together. So if you look at the slide, okay, let me start from the very first one. Now, the skeletal structure of a polyatomic molecule or ion indicates the order in which they attach to one another. Now, let me give an example of this one to show you a polyatomic. C4 has 5 atoms. It is polyatomic. 1 atom of carbon and 4 atoms of hydrogen. Now, this molecule, as is presented, gave us an idea of how the atoms or how the molecule is presented. Atom, carbon being the central atom in this case, and in most cases, the central atom is always written first. In most cases, I will tell you where the exception lies. Then these are the terminal atom. The hydrogen are the terminal atom, while carbon is the central atom. For us to understand this, I will want us to look at the rule again. So there is always 1 or more central atom, and there is always 2 or more terminal atoms. Now, it is possible for you to have more than 1 central atom. It is possible. We are going to look at instances of having more than 1 central atom, especially with molecules that are acids, HNO3, H2SO4, and all the likes. You can have terminal atoms and central atoms that are more than 1. So a central atom is bonded to 2 or more atoms in the structure. So your central atom can then have 2 or more atoms attached to it. We are going to see specific structure, an example of what I'm trying to say. The terminal atom in the other case can only have 1 atom. It can only be bonded to the central atom. Terminal atoms are often the ones that need only 1 electron to fulfill either doublet or octet. In any case, they would only have 1 bond with which they connect to the central atom. So in writing the skeletal structure, the idea that every atom must be connected to the rest of the structure by at least one bond. So there must be a bonding, otherwise the atom will be standing alone. So in any case, when you are drawing a Lewis structure, to join one atom, either terminal to the central or central to the terminal, there must be at least one bond to achieve that. It is very instructive for us to know that there are some limitations or some number of bonds that each atom or each period, each group in the periodic table can undergo. For instance, if you are dealing with the halogens, that is the group 7, to achieve octet, they need only one electron, so they can form only one bond. So fluorine, bromine, chlorine, iodine will form only one bond in their structure. Though there are some exceptions, we are going to see some exceptions. That is the reason why you see often as the remark, meaning that there are instances in which you can have more than one bond in the case of chlorine and iodine, in the case of bromine and iodine, forming more than one bond. But generally, the common octet rule is for you to have only one bond to form octet. But there are instances in which octet rule fails, and we will talk about that later in the course of the class. Now, for the chalcogen, which is the group 6, you have oxygen and sulfur. They have 6 electrons already in their valence shell. So they need 2 electrons more to form 8. So they can form 2 bonds most of the time. But also, there can be instances, especially with sulfur, that you have formation of more than 2 bonds. Then you have the nitrogen group, which is a group 5. They have 5 electrons in the outermost shell, so they need 3 electrons to complete the octet rule, to fulfill octet rule, to get a stable electronic configuration. And those 3 electrons can be shared from other atoms. So in that case, it will form 3 bonds in most cases, especially when it is with nitrogen. In the case of phosphorus, you can have more than 3 bonds. We are going to speak to that and explain the reason why that is the case. And finally, in the case of carbon and silicon will have 4 bonds. Always have 4 bonds, because they have 4 electrons in the outermost shell. They need 4 electrons to complete the valence shell. Now, having established and explained this, what are the rules that guide the drawing of a Lewis structure? The rule number 1 is that you want to attain octets. So the octet rule, atoms will share electrons until they are surrounded by 8 valence electrons. Until they are surrounded by 8 valence electrons. That is the first general rule. But that rule is not absolute. That rule holds for the second full rule of the periodic table, from lithium to fluorine. That rule holds. But when you go to the third rule of the periodic, the third period, which is the second full rule of the periodic table, where you have from sodium, then that rule start to break down, and we are going to explain why the rule breaks down. So if you have they, as previously explained, if you look at carbon, though this structure, this Lewis structure of carbon is wrong, it should be 4 different electron in the 4 region. Now, but because we want to use it to represent the double bond with carbon dioxide, so you have it share for having 4 bonds. In this case, 2 of them shared with oxygen, 1 molecule. The other shared, 1 atom. The other shared also with oxygen, 1 atom, to make 4 bonds for as far as carbon is concerned, and to make 2 bonds as far as oxygen is concerned. Then if you look at nitrogen molecule, you will see that you have the formation of 3 bonds with another nitrogen molecule. You can also have a case in which the 3 bond is with another substance, like you have in the case of ammonia. In the case of ammonia, the 3 bond is with hydrogen, 1 each. So in any case, whether you are using it to establish with a double bond or with single bond, you have a fundamental information that there must be 3 electrons to complete the octet. Then 2 carbon and 1 for fluorine and the likes. Now, so you have that first rule, which is octet rule. Now we are going to explain this rule in more detail when we get to valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. Then the next rule that we need to know is the connectivity of the atoms. The connectivity of the atoms. Now, in knowing the connectivity of the atom, you need to understand that the atoms are arranged in such a way that the central atom is positioned first. The central atom is positioned first. And then you now have terminal atoms. Now, in the examples that we have in front of us, you will see that for molecules, except the ones that are acid, the central atom is written first. Carbon is the central atom here. But in the case of acid, nitrogen is a central atom and 1 other oxygen. We are going to talk about it later. Then here, carbon is a central atom and another carbon. Here, selenium is a central atom because that is a form of an acid or hydrogen related. All hydrogen compound, like if you want to write H2O, oxygen is the central atom in H2O, but hydrogen is the terminal atom, but hydrogen is written first. Hydrogen molecules, you have hydrogen always written first. Now, there is a rule as it relates to central atom, and that is the fact that central atom must be able to take more than 1 bond, more than 1 electron to complete its electronic configuration of octets, electronic configuration of noble gas. So in any case, it is not possible for hydrogen and fluorine. You see that instruction here. It is not possible for hydrogen and fluorine to be central atom because the 2 of them cannot take more than 1 electron to complete their valence shell. Other atoms can be central atom, but hydrogen and fluorine alone cannot be central atom. So there are some questions here. I want to find out if any one of you can unmute and answer some of these questions. Which one is central atom in H2O?
Good afternoon, sir. Good morning, sir.
What is the central atom?
Oxygen.
Oxygen, very correct. Then what about in PCl3?
Phosphorus, the P.
Phosphorus. And you continue like that. Beryllium is here.
What
Now,
was the asking?
beryllium is the central atom here. Sulfur is central atom here. Carbon is central atom here. And iodine is central atom here. In any case, the exception is when you are writing hydrogen atoms or hydrogen molecule, that the central atom is not written first. But the general rule is that the central atom is the one that you write first. Now, beside the rule, after you have written the central atom, you will now position the terminal atom in the 4 cardinal directions, just like you did with the electrons. You must position them in the 4 cardinal directions. You cannot position them probably in the southwestern region. We don't draw Lewis structure in a form like this. I cannot draw Lewis structure and write carbon and write hydrogen like this, hydrogen like this, hydrogen like this, and hydrogen like this. This is a wrong way of writing a Lewis structure. It must be in the 4 cardinal directions. It must be in the 4 cardinal directions. So 4 cardinal direction means that I will put, if you look at all this now, if you look at all this, you have the central atom positioned. That is the central atom, carbon. Carbon is the central atom there. Sorry that the arrow, I need to expand the image in such a way that when I put my arrow. Now, if you look at this, carbon is a central atom here. Nitrogen and this oxygen are central atom in this case because of this hydrogen attached to this oxygen in that case. Then in this case, these 2 carbon are central atoms. So this oxygen is also going to be a central atom because you have hydrogen to it. In any case, we have central atoms as presented in the slide: carbon, selenium, sulfur, and oxygen in this case. Now, you would then position the terminal atoms in cardinal position around it. So those are the rules as mentioned and as presented. If there are questions, probably after some time I would ask for questions. So as previously mentioned, fluorine and hydrogen cannot be central atom. Now, another key issue is the hydrogen atoms that are hydrogen atom are always written first when you are writing for molecules of acid. So you see oxo acid, hydrogen atoms are bonded to the oxygen. They are always written first in hydrogen molecules and the likes of that. So in polyatomic molecules or ion, the central atom usually has the lowest, and that is another rule, very important rule. Now, if you want to look at the central atom, you can determine the central atom by looking at the electronegativity of the atoms that are joined together. The least electronegative is the one that is always a central atom. For instance, if you are writing CO2, carbon is less electronegative than oxygen. If you are writing NO2, nitrogen is less electronegative than oxygen. So in writing molecules, for instance, you want to write BeCl2, beryllium dichloride. Beryllium is of lower electronegativity, so beryllium will be the central atom. So that information is very important. In determining the central atom, the least electronegative is the central atom, except hydrogen. And hydrogen is not central atom. We've already established that. So hydrogen can be the least electronegative, but still not going to be the central atom. Then you can also have a major exception in the sense that carbon catenates. So carbon can form long chain. And because carbon can form long chain, carbon, you can have 2, 3 carbon becoming central atom linked to each other. Carbon can become central atom linked to each other. Now, the next thing is for us to now quickly draw some molecules of this. Now, in also drawing this, you need to understand this other rule. When you want to draw a Lewis structure, you will look at the total number of valence electron in that molecule. For instance, N2O4. Nitrogen has 5 valence electron. Multiply by 2, you have 10. Oxygen has 6 valence electron. Multiply by 4, you have 24. Add 10 to 24, you have 34, which means that N2O4 has a total of 34 valence electron. Now, if your electron is charged, your molecule is charged, like you have in the case of NO3 minus. In the case of NO3 minus, it is a charged molecule. Nitrogen has 5 valence electron. Oxygen has 6 valence electron times 3, making a total of 18. Then the minus that you have on it, which is a charge, means that you have an excess electron. So if you want to calculate the total molecule, you will need to add that excess electron, making a total of 24. 5 plus 18 plus 1, making a total of 24. Now, if it is a positively charged molecule, like you have in the case of ammonium ion, then that is an electron deficient system. Nitrogen will have 5 valence electron. Hydrogen will have 1 valence electron times 4, making a total of 9. Then you will subtract the electron deficient, the electron that has been lost, to make it positive. So making a total of 9 electrons. Now, those total number of electrons are then distributed around the molecule. Now, after you have first established their central atom and the terminal atom. So for the chemical formula that you have, and you want to write the Lewis structure, you can have an ABN system where A is your central atom and B is your terminal atom. The terminal atom that are flanked around A are the ones that will be attached to the central atom. So in this diagram, in this slide, you will see that the blue colors are the central atom. If you look at it, you have nitrogen established a Lewis structure with hydrogen in ammonia. Then in NCl3, you also have nitrogen with chlorine, and NO2, nitrogen with oxygen. And nitrogen is the central atom because it is the least electronegative, except in the case of ammonia. Then nitrogen is also able to take more than 1 bond, but chlorine cannot take more than 1 bond, and hydrogen cannot take more than 1 bond. In this case, so you have nitrogen as your central atom. So when you want to write this, nitrogen becomes what you are going to write as a central atom. Then you will now go and add your other molecules onto it in that. So if it is Cl, Cl, and Cl in that order, then in any case, after you have done that, you will need to also do some other things, which is now distributing the electrons around the shell. In this, we have already said that hydrogen and fluorine can never be central atom. So after you have written, you will need to write the skeletal structure, which is what I just wrote and clean up. Then you will now position your electron around the shell. So what does that mean? Let's look at, I would not want, because of time purpose. Now, you have to place your electron. You have to place your electron around what you have written. That is another procedure. You place your electron around. Now, for each bonding, you have one pair of electron for each bonding. And then the rest that are non-bonded, you can then have them as lone pair of electron around both the central and the terminal atom. Now, if you have fewer electrons, when you start to distribute your terminal electrons around your terminal electron and central electron, if you have fewer electrons, it means that there is a possibility of multiple bond, either double bond or triple bond. Let's just quickly, this step is repeating all that I've said. Everything I've said is what is represented in this slide. I will not dwell on it. So let's look at this example. We want to write the Lewis structure of NF3. In NF3, the central atom will be nitrogen. And the reason why nitrogen is the central atom is, number one, it has lower electronegativity compared to fluorine. Then it is also, we also know that fluorine cannot be the central atom. So in this case, you have your nitrogen in that form. Sorry that I mentioned that you would position your terminal atom in the cardinal of your molecule. But in this case, because you have you don't have four cardinal position, you will position it as presented. Because when we get to valence shell electron pair repulsion theory, I will explain the reason why it is positioned in that form and not in a triangular or a T structure form. Now, having established that your central atom is nitrogen, you will then flank it with the 3 electrons. Then you will now calculate the total number of valence electron. Nitrogen has 5 valence electrons, so you have 5 there. Fluorine has 7 valence electrons, and there are 3 fluorines there, so you have 21 there. And if you add everything together, you will have 26. Now, the 26 would then be distributed around your molecule. Now, it has 3 bonds. Those 3 bonds are 3 pairs of electron, making a total of 6. So you need to look at how to distribute the remaining 20 out of 26. Now, we will start with the central atom and check if it has formed octet. Now, if you look at the central atom, the octet of the central atom is not formed because you have 6 electrons around it. You have 3 bonds, so 6 electrons around the central atom. Then it means that you need a lone pair to make it 8. So you will see a lone pair there. Let me probably expand for better visualization. Now, if you look at this, you have 1, 1, 2, 3, 4. 1, 2, 3, 4. 3 bonding pairs and 1 lone pair, making a total of 8. So nitrogen is complete with that single lone pair. Then for each of the fluorine, they have 1 bonds, making 2, and they need 8 to complete. So you have 1, 2, 3 lone pairs on each of them. So each lone pair is 6 electrons. So 6 electrons there, 6 electrons there, 6 electrons there, making a total of 18, plus the lone pair of electron on nitrogen, making a total of 20, plus the 3 electron pair, making a total of 26. Now that shows us that we have a complete Lewis structure drawn. If you draw your Lewis structure and you end up with this, you have not correctly drawn your Lewis structure because your bondings are not, your electrons are not represented. You have to get to this point before you are finished drawing your Lewis structure. Now, another important example is the one where you have carbon as your central atom, and you have your other molecules. So you will go and try your hands on this. In this case, carbon has 4 electrons in the outermost shell. The 2 fluorine has 14 electrons, which is 2 times 7. The 2 chlorine has also 14 electrons. If you had everything together, 14 plus 14 is 28 plus 2, that's 32. So you will have your chlorine in this, your carbon in the center, your chlorine atoms and fluorine atom as terminals around it. Then your carbon has 4 bonds, making a total of 8. So you do not have a lone pair on carbon. Then each of your terminal atom will need 6 bonding electrons, which is 3 lone pairs. So 6 bonding electrons in 4 places, that gives us a total of 24. And the central, the central atom also have 8. 8 plus the 24 makes 32 that you have there. Then when we have example of double bond. No, this one does not have double bond. So I will not need to dwell on this. But to explain that in this case, you have 2 central atoms, carbon and oxygen, because there is another terminal atom attached to oxygen. So that makes it 2 central atoms. So in drawing this, you will also calculate the total number of electrons. The total number of electrons in this case is 14. 4 plus 6 plus 4, 14. Then you have carbon and oxygen as your central atom. Attached to carbon is 4 hydrogen atoms, making a total of 8. That is complete. Attached to oxygen is also 1 hydrogen, and this, so making a total of 2. So this total of 2, we have 1, 2, 3, 4, 5 bonding electrons. 3 to hydrogen and carbon, and 1 to oxygen, 1 to hydrogen and oxygen. 1 to oxygen and carbon, 1 to hydrogen and oxygen. So that is a total of 10 bonding electrons. The total number of bonding electrons here is 10. And you have a total number of electrons to be 14. So which means that you have 2 unbonding electron, 2 lone pairs of electron. So which is 4 unbonded electron, which are 2 lone pairs of electron. Take note that when we are putting the unbonded electron, we put them in pairs because they must be lone pairs. They must be lone pairs. Now, as we get towards the end of the class today, when you have a multiple bond, you will likely have if a system that is not filled. Now, take for instance, we want to write the Lewis structure of C2H4. The bonding electron, the total number of electrons in the valence shell is 12. 2 times 4 of carbon and 1 times 4 of hydrogen, making a total of 12. Now, if we want to now draw that, carbon at the central atom, so you have 2 carbon, and I have 4 hydrogen, so I will flank the 4 hydrogen around it. So I have a total of 5 bonds. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 bonds, that is 10 valence electrons. That is 10 bonding electron out of the 12 valence electron. So if it is 10 bonding electron, I cannot put the remaining 2 on carbon. Carbon will not exhibit lone pair. If I put the remaining 2 on this carbon, if you count the number of electrons on this carbon, you will see that it has gone beyond, it is complete. You have 1, 2, 3, 4, which is 8. But this one has 1, 2, 3. So this one has deficiency. So that what that means is that there is 1 electron here and 1 electron here. And if you have 1 electron and 1 electron here, that means you have a double bond, a pi bonding system. So anytime you have that deficiency in putting your Lewis structure, it means that you have that kind of double bond. And the same is explained also here. You have lone pairs, you have electron. If you look at here now, this nitrogen has 1, 2, 3, making 6. This one also have 1, 2, 3, making 6. It's not complete. But when you now have it as 1, 1 on each, you have 1, 2, 3. Those are 6 bonding electron, and you have 2 here, making 8, 2 here, making 8, making a complete system. So this is a convenient point for us to end. This is the end of the note. I wouldn't know if there is anybody with 1 or 2 questions. I will quickly entertain that before I stop the class. If you have questions, just raise up your hand. I will just entertain 1 or 2. Okay, Ogini, Victor, unmute and ask the question.
Good morning, sir.
Good morning.
Sir, how can I draw the structure of Al2Cl6, the Lewis structure of Al2Cl6?
Al2
Cl6.
That is a different. That is. We will get to that when we get to valence shell electron pair repulsion theory, because if you look at Al2Cl6, it does not follow octet rule. Cl6 around Al will not follow octet. So we will discuss that when we get to electron pair repulsion theory.
Okay.
Photo. Okay, if Photo is not ready, Adelaja.
Good morning, sir. Good morning, sir.
Okay.
Good morning, sir. Thanks, sir, for the privilege, sir. So, what I want to say is that it is the total number of electrons that determine the structure of the Lewis structure. Like in the case of this nitrogen now. So since the 10 will not favor the single bond, so it will favor the triple bond.
That is very correct.
Okay,
because
sir.
if you look at the 10, in distributing the 10, you will never see octet for each of them if it is a single bond.
Okay,
so
sir.
You would then go ahead to add the rest.
Yes. So it's favor both both atoms. Thank you, sir. I really appreciate it.
You're welcome. I will only allow for Adelaja. Okay. Let me allow for Adelaja and Eniola. Quickly, ask your questions. Adelaja. I can't hear you. Okay, Eniola.
Good morning, sir.
Good morning.
Good morning, sir. Can you hear me, sir?
Yes, I can hear you.
Thank you for the privilege, sir. Sir, about this nitrogen, can't we leave it as nitrogen, single bond nitrogen with all these other lone pair? Sir,
I didn't get the question very
can you hear me,
well,
sir?
but if I may,
I said,
okay, go ahead.
I said for the level structure of this nitrogen too, can't we leave it as nitrogen single bond nitrogen, then all this lone pair by the side? Must it
If
be
you
that
look
we
at the lone
convert it
pair, if
to
you look at the lone
nitrogen
pair
triple
with a
bond?
single bond, sorry, if you look at the lone pair with a single bond,
Yes.
count the number of electrons on each of the nitrogen. How many are they?
4 now.
The number
6,
of
sir.
electrons on each nitrogen. How many?
On 6, sir.
6. Is that octet?
Yes, sir.
That is
No,
not
sir.
octet. So, which means that it will not, it won't be correct to leave it like that because it has not achieved octet. And nitrogen molecule achieve octet. So, in any case, this is a wrong drawing. This is the right one. Okay, this will be a convenient point for us to end the class. We will meet again on Monday.